let's get started. So the first thing, I just want to quickly remind you that I chose to have office hours from 9 to 11 on Wednesday and Friday. I understand that some of you probably have classes during those times. If that's the case, that just feel free to send me an email and we can make some arrangement for you to get help. It's going to be over Zoom. That's the Zoom link. In the future, so this is the home page when you go to the Math 527. In the future, if we cannot meet in person, if we have to meet over Zoom, this will be the same Zoom link that we're going to use. Just in case you know where to find it. Have you started working on the homework yet? Okay. Anyway, so if you haven't, no problem. It's not due tonight. It's due Sunday. It's again just the bottom of that page. There's a homework one there. So it's if you haven't started, maybe take a look at the problems at some point. Don't wait until the last minute. If you have any questions, we can spend 5 to 10 minutes on Thursday to go over them. Okay. So like I said, I don't mean to give you pressure. You don't have to finish it tonight, but it just keep that in mind. All right. Any other questions or comments? No? All right. If you don't have anything on your mind, I guess I'm just going to begin with a few examples I took from the textbook. So the examples I'm going to go over today are linear ODEs that in the form of dy dx equals a function of x, y. But we're going to begin with a simpler example. So I'm going to call this the first type of problems, which is the differential equation looks like dy dx equals a function of x. The right-hand side is only a function of x. There's no y there. This is basically saying is, you know, equivalent to be saying like y prime equals a function of x. Right? How do you solve a problem like this? Well, to solve for the y, so to find solution, y really is y in the form of y equals f of x. So if we want to find the solution in this case, we just find the antiderivative of the right-hand side. The example is if we have, so suppose we ask to solve dy dx is equal to sine 5x for y of 0 equals 2. So if you look at the differential equation given here, dy dx equals sine 5x, I believe you have seen that before, right? In the past, it's really just, okay, what is the y, right? If you know the derivative of y is sine 5x, what is the y? Well, to find the y, we just find the antiderivative. Do you remember the antiderivative of sine? Yeah, you do. Cosine? Close. Negative cosine, exactly. So the antiderivative of sine is negative cosine. But then because we have 5x in the sine function, right, we have to use substitution, which I'm not going to do. So you can use substitution. I'm going to leave that to you. So if you use that correctly, and it really just ends up to have an extra 1/5 as a constant in front of the cosine. So what I did in my head is kind of like, okay, I want to find the antiderivative of sine, which can be cosine, but the derivative of 5x is 5, but I don't want 5. I want the opposite, so 1/5. kind of just try to think backwards, I guess. And a plus a constant c. So this is the general solution. And the general solution is in the form of y is a function of x, right? So this is the y equals a function of x. That's the form of it. In this case, we call this solution explicit. So this is the solution is in explicit form. Or just explicit solution. In a couple of minutes, we're going to look at some solution that you cannot put in this form. You might just have to leave it as a y squared in there. That's an implicit form. Okay, so the next step is we given the initial condition, we have to figure out what the c is, right? So use initial condition y of 0 equals 2 to find c. That's going to be just plug in 0 for x, 2 for y, so 2 equals negative 1/5 cosine 5 times 0 plus c. It turns out, I'm just going to do it quickly, but you should be able to find out the c there. It's 2 and 1/5. So at the end, y equals negative 1/5 cosine 5x plus 2 and 1/5. Questions? So let's just want to show you this is the first type of questions. If you have dy dx on the left, y is a function of x, and then you have a function of x on the right. Really, we just find the antiderivative. That's something we have done before, right? Now, here's the second type of problems. The left side, we still have dy dx, so y depends on x. But the right side, instead of having a function of x, we have a function of y. This case, we cannot find the antiderivative directly to solve for y. So we have to do something. So the first thing we have to do, we're going to flip both sides. To get dx dy is equal to 1 over f of y. So when we flip both sides, we're basically switching the independent variable x, make it dependent. So x depends on y, and this is also depending on y. And then now we can find the antiderivative. So then find antiderivative. So here's the example. We're going to solve dy dx equals y cubed for the initial condition y of 0 equals 1. So if you look at it, the given differential equation says, okay, y depends on x, but now we have y, so we don't know what y is, right? If we don't know what the y is, we can't really find the antiderivative with respect to x there. So the first step, I'm going to flip both sides, so I get dx over dy is equal to 1 over y cubed, which is just y to the negative 3 in the exponent. Negative the power. And then now we can actually just find the antiderivative. The left side will give us x, because x is the dependent variable. So x equals the antiderivative of y to the negative 3 dy, which becomes y to the negative 2, 1 over negative 2 plus a c. Any questions on that? And then remember that, keep in mind that we had y as a function of x to begin with, right? So over here it says that y, we want to have at the end y equals a function of x as a solution. So that's what we want to find, if possible. But here we have x equals some function with y, so we kind of have to isolate the y from here. Just rearranging them, rearrange the terms, minus c to both sides. We get x minus c equals 1 over negative 2, y to the negative 2. Multiply by x negative 2 to both sides. We get negative 2 x minus c equals y to the minus second in the exponent. Flip both sides to make the exponent positive, so we get y squared equals 1 over negative 2 x minus c. So what I did at the very end is that I flipped both sides to make this a positive exponent. That will become the denominator. Questions? So this one, it's usually we leave it in this form because if we were to kind of solve for y, there would be two possibilities, right, for y. So if we were to solve for y here, we get y equals positive 1 over square root of negative 2x minus c, or we can have y equals negative 1 over square root of negative 2x minus c. Instead of writing those two possible solutions, we just leave it the way it is with the y squared. We don't want to kind of break down into different cases there. And this is what we call the implicit solution, because it's not in the form of the y equals some function of x. You probably saw that before, right? Like in geometry or maybe algebra class, like if you have the equation for the circle, you have x squared plus y squared equals 4, right? That's the implicit equation. It just means that we don't have y equals something. Before I move on to find the specific solution, I kind of just want to bring your attention to this, the beginning, what we did. So over here, what we did is we flipped both sides, right? When we do that, we kind of assuming that y cannot equal 0. So assume y cannot equal to 0 there. When we flip both sides to make the y the denominator. And at the end, the solution we found is for the case that y cannot equal to 0. But what if y actually equals 0? What is the solution to that differential equation? So case when y equals 0, what is the solution to the differential equation? So basically we need some y. So we need some y that will satisfy this differential equation, right? So that's the differential equation we want to satisfy. So what is the y function that will satisfy it? It's not easy, but it's just kind of based on experience. It turns out that the solution is also happen to be y equals 0. So y equals 0 happen to be a solution. We can check if y equals 0, we want to know if it satisfies this differential equation. To check, we have the y, that's going to be 0. We also need the dy dx. So if, assuming that's a solution, we can take the derivative, dy dx, So that's going to be 0. And if we take those two values, we're going to put in the differential equation. This side becomes a 0 because dy dx is 0. So y cubed is also going to be 0 cubed. So we get 0 equals 0 cubed. So that's going to be 0. So just, I guess, just based on experience and what other people generalize, the y equals 0, it's a solution for that differential equation. But is it a solution that satisfies the initial condition? Well, then we have to check. So for now, we just know that solution to the differential equation could look like this, y equals 0. It also could look like this one. So let me just write it down. The general solution to differential equation dy dx equals y cubed is y squared equals 1 over negative 2x minus c, and y equals 0. So both of the solutions will satisfy it. But we want to find the specific solution. So the next step, we're going to use initial condition, which is y of 0 equals 1. Let's check the easy one first. Let's check this one. Well, x equals 0, y equals 1. This one says x equals 0, y equals 0. So that's not going to give us a specific solution. So we can just ignore it from here. Does that kind of make sense? So y equals 0 doesn't satisfy initial condition, so we just ignore it. Let's try the other one. For this one, we're going to plug in x equals 0, y equals 1. If we do that, put it in. We have 1 squared equals 1 over negative 2, 0 minus c, and it turns out that c equals 1/2. Therefore, the specific solution at the end is y squared equals 1 over negative 2 x minus 1/2. Questions? And this is not a great example I picked, because it turns out that this specific solution is in implicit form, right? And it turns out that you can actually find the explicit form to this specific solution at the end. Because if we were to kind of go from here, find the two cases, right? Take square root. We have y equals positive 1 over square root negative 2x minus 1/2. And then we could also have y equals negative 1 over square root of negative 2x minus 1/2. Okay, could both of them be the explicit solution, satisfy the initial condition? Could be. It turns out that if we kind of just apply the initial condition to check, so if we take x equals 0, put in there, x equals 0, put in there, we get a positive 1 in the square root, so we get positive 1 here. So y equals positive 1. That's good. So that solution satisfies the differential equation, satisfies the initial condition, right? What about this one? If we put 0 here, this entire fraction will become 1. We get y equals negative 1. X equals 0, y equals negative 1. So that tells us that this is not going to be the solution that satisfies initial condition and the differential equation. In the end, it turns out that for the given initial condition, this is the only solution we can have, and it's explicit. But if, like I said before, it's, if you kind of just stop here, there's nothing wrong with it, right? That's the implicit solution. If you kind of want to take a step further, you can find the explicit solution. There's only one. Hopefully you don't run into those cases. Questions? Yeah.
So if the question asks for what the interval will be for the solution.
Okay, that's related to the homework, I think. Can I answer that on Thursday?
Yeah.
I'll definitely spend some time touch on that part. Good, that's a good point. But if this, for example, if this question says find the implicit solution, you can just stop right here. You don't have to do anything further. But if it says find the implicit solution, then you can have to go all the way to this point. Any other questions? Yeah, if you have questions from the homework, don't worry too much about it now. I'll definitely spend some time on it next time. Good point. Okay, so, all right, with that said, we can look at the next type of questions. So, the next type of problem is that on the left side you can have dx, dy, dx, but the right side has a mix of x and y. It's not just x or just y, now it's mixed. And then more specifically, we want the case that we can write the right-hand side as a function of x times a function of y. If that's possible, if we can just take the whatever this side is, we can write in this form. If that's possible, then we can use this called separation of variables. To solve for the function y. If you cannot write the product, then this technique probably won't work. So here's the example. Oh, maybe I should take a step further, sorry, before I give you the example. So to use separation of variables, so the first thing we're going to do is that we're going to move the function of y, the gy, and move it to the left. So that will give us 1 over gy dy dx, and then that's going to equal to f of x. So if we have them in the product form, we can take one side, divide it to the left side, assuming that gy is not equal to 0. And then what we're going to do is that we're going to move the dx. So here we have dy dx. We're going to split that and move dx to the other side. So we get 1 over gy dy is equal to f of x dx. So now we have the left side is a function of y and the derivative of y with respect to y. And we have a function of x, the dx. We can integrate both sides. And then when we integrate, this side is just going to be some function of y. That's it. This side is going to be some function of x plus a constant. But that's kind of the the two main steps in using separation of variables. You want to separate the variables y from the variable x. So here's the example. We have f, so we're going to solve x prime equals t over 3x squared plus 1 when the initial condition is x of 0 equals 1. So the first thing I'm going to do is just make it look easier. So I'm going to rewrite x prime as dx dt. Dx dt equals t over 3x squared plus 1. The next step, so I'm just looking at it, it seems like here we have t in the numerator and then we have the function of x in the denominator. I can separate that as a product. So what I'm going to do is I'm going to rewrite this as t times 1 over 3x squared plus 1. So here we have a function of t times a function, I'm just going to call this f of t, and this is a function of x, I'm going to call it gx. Right, the right-hand side we can separate it as a product. And I'm going to move the function of x on the left, leave the f of t. And that will become, when I move the fraction with the x in the denominator to the left, I get rid of the fraction, so I get 3x squared plus 1 dx dt is equal to t, and I can move dt to the other side. To be honest, you can just do it in one step, but just keep it separate for now. 3x squared plus 1 dx equals t dt. I want to point out that we are really not multiplied by dt. It's, we just say, okay, that's with respect to x. We want this side to be with respect to t. And then we can integrate both sides. So that will give us, if we integrate the left side, we get what? We get x cubed plus x plus a constant c, we call it c1. And the right side we have this t squared over 2 plus a constant c2. Separation of variables always give you two constants, because you have two integrals. It's really not necessary to write both. In the future, you could just say, just drop this constant on the left and you keep a constant on the right. You don't need to keep two constants there. It doesn't really make a difference. You can just call it c. And that's it, right? It's, if we want to solve for x, so we want x equals a function of t, it's probably not going to be easy. I just leave it there. And this is going to be the implicit form. And the rest is about finding c. And we can use the initial condition plug-in directly. So we get x equals 1, t equals 0, right? So we get 1 plus 1 equals 0 over 2 plus c, and c equals 2. And at the end we have x cubed plus x equals t squared over 2 plus 2. Questions? I kind of want to go back to a previous problem we did, and to show you that if you want to use separation of variables, you can still make it work. Any questions on this particular example? All right, let me go back to one of the, I think it was the second example, when we said, oh, if you have f of y on the right-hand side, you have to flip both sides, right? We don't have to flip both sides. So let me rewrite the problem. So earlier we want to solve, so recall example 2, we want to solve dy dx equals y cubed. You don't have to flip it, you can just use separation of variables. So what we're going to do is that here we have a function of y, there's nothing else, right? We can assuming that there's a function of x, which is just a constant of 1. So let's just assuming there's a constant 1 here. And if this is a function of y, this one we can just say, oh, that's a function of x. But it's not, it's just a constant. And then we can move the function of y to the left. So that will become 1 over y cubed dy dx, but I'm going to move dx to the other side. So that's a 1 dx. Is that okay? By using separation of variables. So the y function is on the left, dy is on the left, and then the constant 1 is on the right, and the dx is on the right. You don't even have to write the 1 here, you just assuming you know that's a 1. And then now we can integrate both sides. So the left side, if we integrate, we really integrate y to the negative 3, so we get 1 over negative 2, y to the negative 2, and on the other side we have x and a plus a constant c. And it turns out to be the same expression, well, slightly different, I believe. So compared to, I think it was like a x equals 1 over negative 2y to the negative 2 plus c. This is what we had before. This is what we have now. It really doesn't matter, because if you move this c to the left, it becomes x minus c. But minus c and plus c are really the same. It's just the c is different. So I just want to show you that either way, you're going to end up with the correct solution. You have multiple techniques that you can use. Depends on the type of equations. Questions? Okay. All right, let's practice one more problem here. So here we want to solve xy prime equals y plus 2x squared y, where y of 1 equals 1. So what do we do first? Well, one thing is this example is different from all the examples we did before, right? Because here, all the examples we did is like dy dx or dx dt. But here we have an extra x here. Let's get rid of that part. So let's divide by x on both sides. So we got y prime by itself is equal to y plus 2x squared y over x. And I'm going to note here, because I divide by x, right? So I'm going to note x cannot be 0 in what I did. And on the left side, I'm going to replace the y prime as dy dx. So I have the derivative of y on the left, and then I have this function, there's a y, there's an x, all mixed in there. So perhaps we could maybe try separation of variables when you have both x and y, right? So try separation variables. So we need to take all the y and then separate it away from the x, right? So we're just going to really just back out the y. We can take out y from here, also from here. So we end up with y times 1 plus 2x squared over x. So now the function of y is on the left, and the function of x, I'm going to call it g of x, it's on the right. It's separated, and then we got a product of them. The next step in separation of variables is that we have to move the y to the left and move the x to the right. When I do that, I have 1 over y dy is equal to 1 plus 2x squared over x is still there, and the dx. Just double check. Here we have a function of y dy, no x there. Here we have a function of x, dx, no y. That's good. And I'm even going to take a step further by rewriting the right-hand side by simplifying the fraction. So the right-hand side, I'm going to write it as 1 over x plus 2x squared over x. That's 2x to make it easy to integrate dx. The left side is the same, 1 over y dy. I think it's easy to integrate in this way. Integrate both sides. The left side, I have if you recall that integral of 1 over y is natural log, right? With the absolute value sign. And on the right side, again, the first term is also a natural log absolute value of x plus x squared plus a constant. We want to have a function y. Y is a function of x, so we just add a base e. That's what I always do if I have a natural log. And that will become absolute value of y equals, this is the e to the natural log of absolute value of x. And I'm going to split those terms because they're all in the exponent of e, so I'm going to write it as a product. So that's first term times e to the x squared times e to the c. To simplify further, e to the natural log of x is absolute value of x. E to the x squared is e to the x squared. And the e to the c, which sometimes we like to use a different constant there, because e to the c is a constant, so we're just going to call it d, if you're okay with it. It's just a constant. D is equivalent to e to the c, which is positive, by the way. And then, any questions so far? So over here, what I did is if you remember, if you have a sum in the exponent, that really becomes a product of the same base. That's what I did. And then what I did is I called this a new constant d, and I simplified this part by getting rid of the natural log and base e. The middle part I leave it. And then the next step is that you look at it like, oh, I have an absolute value of y. Is it okay to drop the absolute value? Well, then you look at this side. So here we have d is positive because that's positive. E to the x squared is positive. This is always positive, right? So every value we get on this side is definitely going to be positive. So there's no need to keep the absolute value if we, assuming y is positive. So, well, next line. So y equals this, assuming y is positive. What about this x? Can we drop this x? I guess it depends. If x is positive, that's positive, this is positive, so this has to be positive all the time, right? So if we know x is already positive, then we can drop the absolute value. Just kind of to simplify. You probably ask, what if x is negative? Right? If x is negative, then we have to add a negative sign to make sure this is positive. But for now, that we can just say, okay, the answer is in this form, assuming that y is positive, x is positive. And the d obviously is also positive. Questions? Well, then they kind of going back to that question. So here, this is the general solution for y that's greater than 0. What if y equals 0? So going back to what we had, this is a differential equation we were given. So what if y equals 0? What is the solution? We can guess, right? Maybe we can guess just like before. We can guess the solution is also y equals 0. So we can guess y equals 0 is a solution. And we might get it wrong, but at least that's a guess. So if y equals 0 is a solution, then we know the derivative is definitely going to be 0. Right? Derivative of 0 is always 0. Well, let's see if this satisfies the given differential equation. So check. So if we take the y prime equals 0, put into the differential equation, we get x times 0. Is that going to equal to y is going to be 0 plus 2x squared times 0. It turns out that that's 0. So we get 0 equals 0. So y equals 0 is the solution to the differential equation. So just keep in mind that now we have two solutions, right? So those two both satisfy the differential equation. One is this one, for positive y. The other one is y equals 0. And then the next step is that we need to find the specific solution. We need to know the constant d to find d using initial condition, which is a y of 1 equals 1. We literally just try both, right? When x equals 1, y equals 1, so that y equals 0 definitely doesn't work here. So we don't have to worry about that one. If we put y equals 1, x equals 1 here, we can find d. So we got 1 equals d times 1e to the 1. So we get d equals 1 over e. So y equals 1 over e x e to the x squared. That's the solution. Any questions? So just sometimes to keep in mind that, when you look for the solution, just try, just look at it. Is y equals 0 going to satisfy the differential equation? It's not going to be something complicated. If it's not, then it's not the solution. It's not a solution. I have 4 minutes. I kind of want to quickly talk about how do you plot the slope field. I'm just going to use this example. Y prime equals xy. So that's the same way as writing dy dx equals xy. And if you want to plot the slope field, the first thing we're going to do, we're just going to make a table xy and also dy dx. If you remember that back then in calculus, when we find the instantaneous slope, right, that's just really the derivative. That's what this part says. So dy dx is always going to give you the slope. So this is the slope. And how do we find it? We just pick a random value for x and y. For example, if we say x equals 1, y equals 0, and then we can take this two values put in here to pick up the slope, which is going to be 0. And then if we say x equals 1, y equals 1, and if we put in there, we get 1 for slope. If we pick x equals 1, y equals 2, we can put into that right-hand side, so we get 2. What if we pick x equals 0, y equals 0, then we end up with 0. Something like that. And to plot the slope field, we just graph the xy coordinate. 1, 2, 0, 1, 2, of course with negative values. And then what we do is that we just plot the point and then plotting the slope corresponding to this point. For example, the first point I have is x equals 0, x equals 1, y equals 0. That's this point. At this point, I'm going to draw a small segment with a slope that's equal to 0. So that's going to be a horizontal segment. Just a small segment, doesn't have to be very long. At the next point, 1, 1, I'm going to draw a slope 1. So x equals 1, y equals 1 is this point. I'm going to draw a slope 1. If you remember that slope 1 is 45 degrees, just draw a small segment that's 45 degrees. You kind of just have to eyeball it, right? Do the best. What about the next point, 1, 2? X equals 1, y equals 2. We're going to draw a slope that's 2. 2 is a little bit steeper than 1. So just draw something that's a little bit steeper. And x equals 0, y equals 0, we have a slope that's a 0. And of course, if we have enough points, then we have a field of those segments. It basically tells you of the function, the solution to this differential equation moves in that field. To be honest, you're not going to do a lot of this by hand. So here's what I did by just finding it on the Statmos. So this is what the slope field is if you have more points. And just kind of quickly show you. For example, if this is the actual solution for specific value p 0.4, for that value, if you kind of just say, okay, if I know the initial condition, x equals 0, y equals 0.4, I can trace along the segment to figure out what the curve looks like. That's the point of this. If we say, okay, what if the initial condition is 2, x equals 0, y equals 2, then you can begin at this point and then just move left and right by following the segments to draw the curve. Does that kind of make sense? I know that's a homework problem, but try it. All right, sorry for being a little bit late, and now let you go. And we'll see you on Thursday. Take care. Take care.